This video will discuss the idea of compactness of a surface relative to its Gaussian curvature and its mean curvature. Let's let S be a compact. Of course, this is a topological thing, which means it's a closed surface and the surface is bounded, right, by the Heine-Borel theorem. That's what compact means in Euclidean space. Surface, parameterized surface. Okay. Then there is a point P on S, point on the surface, where the Gaussian curvature of the surface at that point is strictly positive, with Kp, the Gaussian curvature, strictly positive. Okay. At such a point, so the existence of this point, note, the existence of this point proves that compact surfaces cannot be minimal surfaces. Okay, and so how do we prove that, of course, right? So proof of this note over here is that the Gaussian curvature at this point, P, is really kappa 1, P, kappa 2, P, where kappa 1 and kappa 2 are the principal curvatures, right? So since Kp is strictly greater than 0, that means that kappa 1, P, and kappa 2, P have the same sign. Okay, maybe they're both positive or both negative, right? So if K1 of P and K2 of P are greater than 0, that implies that H, which is K1 plus K2 over 2, is greater than 0. And if K1 of P and K2 of P are both less than 0, that implies H, which is K1 plus K2 over 2, is strictly less than 0. In either case, the mean curvature is either positive or negative, and therefore it can't be a minimal surface. Great. And so now it's the idea about how we prove this statement over here. So once we have this statement, we've automatically proven that there's no compact surfaces cannot be minimal surfaces. Beautiful. That's one nice result about minimal surfaces that we get for free, right? It's now it's the idea. So we have a compact surface. A compact surface is bounded, right? So here's your compact surface, right? It's just sort of stuck over here. It can't go to infinity, right? It's in Euclidean space. And so what we're going to do is we know that on a compact set, a continuous function attains a maximum and a minimum value, right? So the extreme value theorem, that's my x-axis, that's my z-axis, and that's my y-axis over here. So here's a proposition from analysis. Prop. A continuous function achieves a maximum and minimum value, achieves a max, respectively a min value on a compact set. Okay. That's easy to prove, right? That's just the fact that the image of a continuous function under a compact set is also compact, okay? And so what we're going to do now is we're going to consider a particular function, right? And so the function we're going to consider is the following. So consider f of a point of any vector v, right? F of v is just going to be the length of v. It's a scalar valued function, right? So this is a continuous function, right? So I want to square this. Let me square it to make my life easier, okay? Okay, so this is a continuous, actually it's a smooth function, right? Continuous function. And so in particular what that says is that this function, this length, is going to be maximized on our surface, right? So f achieves a maximum value on the surface. On the surface S. Let's say that maximum occurs over here to point P, right? P, that's the point at where it's maximized, okay? Call it P. Okay? And then what we do is we look at the position of that vector, like so. Call that vector P, like so. And so now what we know is we know that there's a sphere, right? Since that's the biggest it can be, I can consider a sphere whose radius is the length of this vector P over here, right? So what we're going to do is consider a sphere centered at the origin, right? Relative to this point P. And so what we're going to do is we're going to draw a sphere around there, right? And what do we know about the sphere? It's going to contact that point at that vector over there, right? So that's called like an osculating sphere. And so what we can do is the following. So now, let's call it sigma be the sphere of radius length P over here, right? And so one thing to notice of the curvature of this thing over here, if the radius is that, then the curvature of this thing is going to be 1 over the length of P squared, like that. That's the curvature of the sphere, right? This curvature of sigma. Great. All right. So now what we do, so let's draw a curve for any curve. Gamma, which goes P on the surface. At t equals 0, we have, well, if I plug that curve into here, we have f of gamma of t, right? Is going to be the length of gamma of t quantity squared, right? Which is just gamma dot gamma. We have f prime of 0 is equal to 0. And that's going to be equal to what? That's going to be just twice gamma dot. So this implies that gamma of 0 dot gamma dot of 0 is equal to 0. The second derivative is strictly less than 0 since it's a maximum value. And the second derivative of this thing is going to be gamma dot, which is 1. Okay? And then gamma dot, gamma 0 dot gamma double dot 0 is less than 0, like that. Strictly less than 0. Good. All right, and so now what's the point over here? So this condition over here says that this curve over here is going to be the position vector of the curve, which is going to be P. At that point P, you're perpendicular to all of the tangent directions. So gamma of 0, which is equal to P, is perpendicular to the tangent space. Because gamma dot is any particular one, so it's going to be 0 for anything you wish, right? And now, of course, what do we know? We know that the normal vector, what this gamma double dot is the principal normal vector of that curve. That has to be what? That has to be in the same direction as the normal vector to what? As the normal vector to the surface of the sphere, right? And so gamma double dot has to be equal to what? It has to be equal to P, the position of that thing, over the length of P, with a plus or minus sign for the orientation, right? And so, of course, the same thing is true of this thing over here, right? And so in particular, what have we just shown? We've just shown that what can we say about the Gaussian curvature of the surface of the point? Well, the Gaussian curvature is the normal curvature at the point, right? So our normal curvature, kappa n, the normal curvature of this curve, is either going to be what? Is either going to be plus or minus, well, if I solve this equation over here, this is also going to be a p, so I have p dot p, and then take the, and then p dot, so this over here is going to be p dot p, so that's going to be the length of p, and so this is going to be what? This is going to be plus or minus 1 over this normal over here, length of p, like so. Good. Let's make sure we have the everything correct over here. Yep. Good. And so in particular, what does this show us now? In particular, what this says is that these are the maximum and minimum values, right? So Kn straddles in between the maximum and minimum. So if Kn was this, the maximum and the minimum values would be what? Would both be positive, the maximum and minimum will both be negative, right? So by Euler's result, by Euler's theorem, they're either both positive or they're both negative, right? Either K1 and K2 are both positive, right? If this was a positive sign, or K1 and K2 are both negative, right? So either one of those things has to be the case based on whatever the parity of this thing is relative to the normal vector of the sphere, right? So the essential feature of this is that the second derivative gives me is a measure of normal curvature when I dot that with n hat, right? So if I dot that with n hat has to be proportional to this thing over here, and so we get exactly this squared over here. So in other words, if I dot this with n hat, that's going to give me a p dot p. So I get 1 over p. Good. Exactly. So in other words, what this shows that since the normal curvature is either basically has to have the same sort of curvature as the sphere at that point, right? So 1 over the length of that thing, the measure, right? So we either have two positive directions, or if the normal vector is going in the opposite direction, you just split the sphere inside out and you get two negative principal curvatures. In either case, kappa 1 and kappa 2 greater than 0, kappa 1 and kappa 2 greater than less than 0. In each case, curvature p at that point is strictly greater than 0. So in other words, we can always find a point on a compact surface where the Gaussian curvature is strictly greater than 0, which precludes there being any minimal surfaces that are compact. Thank you very much.